Okay. Hello everyone. My name is William Glavin. This is my course project for CS 522. Um, Today I'll be presenting my work on using unsupervised machine learning to detect and reclassify pitch types using Statcast data. Goal of my project is to explore how clustering and PCA can uncover natural structure in pitch movement and release point data and compare that structure to the pitch labels provided by Baseball Savant. For the practical problem and background, I had to narrow this down a little bit from the proposal, but basically, pitch classifications can lag behind real mechanical changes. Pitchers routinely adjust spin, velocity, shape, and release point. Public pitch labels like Statcast may be inaccurate or slow to update. Machine learning allows us to objectively group pitches based on physical characteristics instead of labels. The goal of the project was to use clustering and PCA to see whether we can rediscover pitch types and spot anomalies. And so this is an example of a pitch movement profile. In this example, this is Cam Schlittler, Yankees pitcher from this year. And this shows average horizontal and vertical break for each pitch type. Movement differences form natural clusters even before machine learning is applied. Provides intuition for what PCA and clustering aim to model. Pitches of different types occupy different regions of movement space. So you're going to see some obvious ones like curveballs are going to end up low. Cutters move side to side. Fastballs can rise. In his case, he throws a lot of high sinkers. This is just to give you an example of pitch visualization. There's a lot of cool data out there right now. And so for the data that I use Baseball Savant StatCast pitch by pitch data. They have data on every pitch. It's a huge library. It's really awesome to use. Data set for one pitcher typically contains about 3 to 4,000 pitches per season. Obviously, that can vary type of pitcher, whether with injuries or fatigue. Key features that I used were velocity, movement, and release point, spin metrics. The data was pre-processed using Z-score normalization and removed a small number of outliers. And so for the data set that I used, was a Yankees pitcher from 2024, Luis Heel. I used two of his pitches just to show the difference between the two. I used his fastball and his slider. And so in 2024, he threw between the fastball and the slider about 2,000 pitches. You'll see that we used about 1,300 fastballs, 700 sliders. Um, and the core features again that were used as far as the StatCast data were velocity, PFX-X, PFX-Z, release point X and Z, and they represent the physical fingerprint of pitch shape. I applied PCA to reduce dimensionality to two components for visualization, which formed the basis for the clustering analysis. So, okay, this is an example with Luis Hill's pitches using PCA visualization. It shows clear separation between the fastball and the slider. PC1 mostly relates to velocity and horizontal movement. PC2 relates more to vertical movement and release variation. The natural grouping indicates machine learning will likely separate the pitches effectively. And so this is an important first check. So even without clustering, it shows fastballs and sliders occupy distinct regions in component space. So it's strong evidence that unsupervised learning should be able to rediscover pitch types. Okay, next we use k-means clustering. In this case, it was run with k equals 2. The data set was limited to 2 pitches. Despite having no labels, it produced clusters that almost perfectly matched the known pitch types. And there was a silhouette score of 0.64, which indicates strong cluster separation. So this is basically showing that fastballs and sliders are physically distinct enough that the model rediscovers them without supervision. K-means partitions pitches into 2 clusters from scratch. The clusters also align closely with the Statcast labels. And yeah, so purely using physics, pitch types are recoverable. Next up was the DB scan. So DB scan is finding the dense clusters without specifying K. So K-means would force every pitch into a cluster. DB scan kind of does the opposite, groups only the dense, consistent regions. treats the irregular pitches as noise. In this case, about 40 outlier pitchers, and those could be any number of things. Sometimes there's a pitch out. If there's a runner, you want to get the catcher in a better position, you throw the ball out. It can also, in this case, actually, this data comes from Luis Heel in May, right before he had some injury trouble. So these could be fatigue related as well. The release point starts to drift. The movement of the pitch starts to drift. This is the type of outliers that they pay attention to track like a injury creeping up. So there was 39, about 40 noise points anomalies. And this offers better insight than k-means generally, since not all points are forced into clusters. So this just adds structure. And then for a release point comparison, fastball and sliders come from slightly different release points. Generally, you want all of your pitches to come from about the same release point to try to confuse the hitter. Luis Heel only throws 3 pitches, basically, a changeup sometimes, but mostly fastball slider, which actually is an anomaly for most starters. You generally want to have 3 to 4 pitches to keep the hitters off balance. The sliders are coming from a lower and more glove side. The overlap explains occasional misclassifications, but also that's just generally where the pitcher is trying to be in the middle of this graph. This confirms mechanical distinctions supporting PCA and clustering results. So we see they were released from slightly different locations. Some pitches end up as borderline and show up as outliers in DB scan. That can be because there's an overlap in release point. So this is a mechanical check that validates that the clusters we found are meaningful. And for the methodology overview, loaded the Statcast data, like I said, for Luis Heel for 2024 season using only fastball and slider. Again, he throws a changeup about 20% of the time. So this was most of his pitches from this year. He had a very successful year, won Rookie of the Year this year. We filtered the fastball and slider only. We use physics-based features like velocity, movement, and release point. And I standardized using Z-score, applied PCA to visualize separability, k-means to show cluster separation, and DB scan to perform anomaly detection, and then compared clusters to labeled pitch types. So we, in the end, were able to see how well the physics align with the classification that they use. For the summary of results, the PCA showed strong natural separation between the fastball and sliders. The k-means clusters aligned very closely to Statcast classifications, and the DB scan captures the same structure but also identifies meaningful anomalies. And the release point analysis confirmed mechanical distinction. So it just demonstrates overall unsupervised learning can successfully distinguish pitch types and highlight deviations. And in conclusion, we learned that machine learning can separate pitch types using physics alone. The clustering supports the reliability of the Statcast labels. DB scan, I was able to identify unusual or transitional pitches. And the approach can extend to more pitch types and multiple seasons. I generally try to use a close only several months to just narrow it down. So this shows the value that machine learning can give with pitch design, mechanics tracking, again, sensing an injury coming up, and your arms can act differently if it's not able to perform. And the data that I used, yeah, Baseball Savant, Statcast data. They have a library called Pi Baseball, which I was able to pull the data from. Scikit-learn documentation. Again, we use PCA clustering and model implementation details and some research on pitch clustering and movement analysis. So yeah, thank you for listening. I appreciate your time. I had a great time researching this project, and I appreciate it. Thank you.